It is also known as the resonant commutation because we are using a resonant means RLC circuit. Uses LC component in series with the load resistance RL. In the first circuit, RL is in parallel with the capacitor. In the second circuit, is RL is in series with the capacitance. As we apply the trigger pulse, based on that one, your current flows to the in the circuit, and you're able to identify what is the ISCR and also what is the VSCR also. So we have to see to that it should be IL should be less than IH. Okay, IL should be less than IH. And this is that is where I have started. Now this is the topic we're supposed to discuss. Here in AC circuits, how it's going to happen? Generally in AC circuits, current flows top to bottom. I explained it. That is given in the waveform. It is current commutation method. What commutation we explained? That is class A commutation method. It is called as a current commutation method, not voltage commutation. It's a current commutation method. The RL and commutating components are so selected that the combination forms an underdamped resonant circuit. That is also I told you. There should not be any fluctuation. There should not be any oscillation. You guys know what I mean by underdamped. We should not have any fluctuation over there. We should not have any oscillation. Avoiding the oscillation. Avoiding the oscillation. So where exactly we are going to use? As we all know that one DC circuits. And DC, whenever there is a DC circuits are there, triggering has to be given and you are supposed to go for the commutation. Basically DC to DC and DC to AC. DC to DC your chopper and DC to AC your inverter. So class A in general it will be used in inverters. Class A commutation method will be used in inverters. Why? Why not class B? Why only class A? Because we need a high frequency operations. See, there is this type of circuits are most suitable for high frequency operations, like in terms of kilohertz. You might have observed in your lab, you have given 50 hertz, 100 hertz, 200 hertz. Even we told you, like a clipping circuit, we are given 1 kilohertz. You keep it and you execute like that. We are told that. So whenever there is a frequency of higher range is required, at that time we are going to use the class A commutation method. Okay. But other than that, we are having one more commutation method, that is class B. But in class B, what we are going to have, we will not have only R. Only R will not be there. Let us see what we are going to have. It's a LC circuit. Okay, we will be having the inductance and also capacitance circuit will be there. So here you can clearly see to that one how exactly it differs with the class A. Class B differs with class A. In class A, your RLC were in series. Okay, or your LC were in series with your SCR. Your inductance and capacitance were in series with the SCR. See the circuit here. See, among SCR, L and C, they are in series here with the thyristor. But when you go for class B, this is your thyristor and L and C are parallel with the thyristor. That is the difference between your class A and class B. Class A, L and C are in series with thyristor. In class B, L and C, that is inductance and capacitance, are in parallel with the thyristor. Now, if that is the case, what may be the difference? How exactly it differs with respect to class A? This LC circuit is across SCR and not in series with the load. Clearly it is mentioned. LC, L and C, they are across the load, not in series with the thyristor. That is the first difference. Second difference, as EDC is applied, assume VDC or EDC. Here it has been given as VDC. Now I will consider this as a EDC. When it is applied, thyristor is in positive, it's one forward bias. Even the LC is also in forward bias. Assume that one capacitor is positive and negative. Positive on the other top side and negative on the bottom side itself. So capacitor is also in forward bias. Your thyristor is also forward biased. But compared to capacitor, thyristor will work only when we apply the IG. Until we don't apply the IG, thyristor will not be in forward bias. We should have a firing angle, we should have a triggering angle, we should have a triggering pulse. then only your thyristor will become charged. It's going to activate. So as soon as you apply the VDC or EDC, your capacitor starts charging because it does not have any constraint. Automatically it can start. But in the case of thyristor, it is totally depending on your IG. As until you give IG, that is your gate current, thyristor will not be active. Not be active. So as soon as you give your IG, until you don't give IG, capacitors keep charging. Capacitors keep charging over there. IG now kotte illa, IG now touch madilla, open circuit ide antandre, it will not go, your thyristor will not be active at all. But capacitors keep charging over. As EDC is applied, the capacitor starts charging up to what? Up to the maximum what you are given. Up to maximum. So up to EDC. If the EDC is 5 volts, up to 5 volts, it keeps charging over. Okay. So when the thyristor is triggered, the last statement, next statement, when it is, I have to give the IG. Then only thyristor will be triggered over there. Until you don't give the IG, thyristor is not triggered, not on, not active. Okay. So when the thyristor is triggered, the circuit current flows in two directions. See here. The circuit current flows in two directions. Previously, it was flowing in only one direction. Which direction? The capacitor direction. Now, the circuit current flows in two directions. Because the thyristor also triggered. Because the thyristor is also triggered, it is flowing in two directions. So, circuit current flows in two directions. Which is the direction? We should know that one. In which direction? It starts from EDC, EDC positive, then it will go to thyristor, then it will go to RL circuit. That is RL means your load. See the load here. Here. See, it starts from positive of EDC, then it comes to thyristor, then it comes to RL, then it will once again go back to EDC negative. EDC positive, then thyristor, then RL and EDC negative. This is the first direction, first current flow. Second one, capacitor positive, L, thyristor, capacitor negative. This is not minus. Don't think it is minus. It is a direction it is showing over there. EDC, next it will go to thyristor, next it will go to RL, that is load resistance, next it will go to EDC minus. That is first current flow. The second current flow is capacitor positive, then inductance, then thyristor and capacitor negative. Correct, Alva? See here. If you want, I can write the circuit. I'll just write the thyristor and the circuit. See, here I am switching on my EDC. This EDC positive. So current flows in this direction. First one. Okay, the first two directions showing up. The first direction is like this. So it starts from EDC plus, then thyristor, then go for RL, then EDC negative is going up. Second one is start from here. Plus, that is C, L, this is plus, this is negative. From here, okay, I will not write in this direction. Let me start from CL plus, then go L, then go thyristor, then CL negative. So the current, it is flowing in two different directions over there. That is what is mentioned. The current flows, the circuit current flows in two directions. So this is the direction. This is the first current, this is the second current is flowing on. One will be in clockwise, other will be in anti-clockwise as per the image. As per the image. Okay. When the capacitor C becomes completely charged, as the current flows, what happens now? Completely charged. Then immediately it should get discharged. Okay. When the capacitor C becomes completely discharged, it starts getting charged with a reverse polarity. Assume that one capacitor is getting discharged. So it should once again start charging over there. Due to the reverse voltage, a commutation current IC starts flowing in, which opposes the load current IL. Obviously. See in the circuit, we are having IL. It is flowing in this direction, IL. But IC will go discharging. It is discharging. It's going in the other direction. Get in, get in. IL is flowing in this direction, top to bottom. Capacitor is charged, totally is charged. It is going for discharging. When it is going for discharging, it will be in the opposite direction, the current will flow. The opposite direction, the current will flow over there. Once the charge discharge in the opposite direction, it's going to flow. So IL is coming in this direction, IC is going in this direction. Opposite direction, it will go further. This is IL, this is IC. So both are in opposite direction. Due to the reverse voltage, the commutating current IC starts flowing, which opposes the load current IL. If IC is greater than IL, assume that capacitor current is greater than IL, the resistor is turned on. Obviously, yeah. This is IC, this is IL. IC is more than IL. It is a reverse current is going over there. The reverse current itself, this is going to be turned off. It's going to be turned off. It's going to get an open circuit over there. So when IC is greater than IL, thyristor is turned up. So once the thyristor is turned up, once again the current flows through the capacitor. See, IL is coming like this. IC was also coming like this initially. Once it is charged fully, it is discharging. During the discharging time, IC will go in this direction. IC will be, because it is discharging, it's going in this direction. So IL and IC is getting opposed, so it's going to get open circuit. Once it is open circuit, this is open. Resistance is getting open. So IL will not flow in this direction. I cannot flow. So current will flow in this direction. Once the current flows in this direction, it is getting charged. Initially, it is charged, fully charged. Once it is fully charged, it is starting discharging over there. During the discharging time, IC will go in opposite direction, so the resistor will get open. So the resistor is on, being on. Initially, capacitor is already charged. Capacitor is already charged. Capacitor is getting discharged. Once the capacitor is getting discharged, T will go for off state. T will go for off state. So T is off now. So current will not flow in this direction. Current cannot flow in this direction. Current has to go to the other path. So once it is going to the other path, it is in positive direction. Capacitor charging once again starts. Capacitor discharged. Thyristor is off state. Since thyristor is off state, current cannot flow in this direction. Current will flow in the other direction. Once the current is flowing in the other direction, capacitor starts charging. Capacitor is charging, fully charged. It is discharging. At the time of discharging, thyristor is off. When the thyristor is off, once again capacitor is charging. So charging, discharging, charging, discharging, charging, discharging is going to happen for the capacitor. So capacitor again starts getting charged to its original polarity through the load resistance, load and RL. Still people are coming, or shall I close the door? They'll come, or only this much? Shall I close the door? So current flows in two directions. Two opposite directions are there. One is in positive direction, other is in negative direction. So once these two comes into picture, thyristor gets open. Once the thyristor gets open, once again capacitor starts charging. So it becomes clear that the thyristor after getting on for some time automatically gets off. Thyristor initially will be on state, after some time it will go for the off state. Initially will be on state, then will go for off state. After some time, it will once again go for the on state. Means capacitor is getting charged over there. Charging, discharging, charging, discharging. When the time of charging, on state, time of discharging, off state. So like this, on state, off state, there is also goes on and off. it again gets turned on. It will be on, it will be off, it will be on, it will be off. So like your AC. Here what happens? It is not, we are not given the AC power supply. We are given the DC power supply. If it is AC power supply, automatically it was happening. Since it is DC power supply, I need an external circuit. External LC circuit is required for charging and also discharging. That is called your class B commutation method. Okay. This process is continuously it's happening. The desired frequency of on and off state can be obtained. Very, very important. See, theoretically we know this is what is happening. But when you want to implement that one practically, what should be the L value? What should be the C value? What should be RL value? Because thyristor is fixed. Thyristor is fixed only. But we are selecting the L and C. We are selecting the load resistance. By properly selecting the load resistance, properly selecting the L and C value, we will come to know what will be the T on time and what will be the T off time. What can be the T on time? What can be the T off time? See, capacitor is very high. The capacitor value is very high, 100 microfarad. Assume microfarad itself is high because we are having in the range of 100 nanofarad. We are having 1 nanofarad is also there. 1 nanofarad is very, very small compared to microfarads. Okay. So if the capacitor is high, charging time also it takes more. Charging and discharging. Okay. If the capacitor is very small in size, charging and discharging time is very slow. Very fast it's going to be charged, very fast it's going to be discharged. So basically, we have to select a proper capacitor and also inductor, the L value. By suitably selecting L and C value, we are in a position to check what can be the T on state and T off state. Okay. So that is what has been mentioned. The process is continuous. The desired frequency of on and off state can be obtained by designing the commutating components as per the requirement. So depending on our requirement, how much it should be charged, how much should be discharged, we have to know that one. It all depends on the customer's requirement. So based on that one only you can go for it. See, example what they have given is UPS. UPS only is the example. How much we have to go for it? How much fast it has to be charged? How much fast it should be discharged? The main application of this course is DC chopper circuit. Chopper circuit, you have done that one, DC to DC conversion. That is what chopper, DC to DC conversion. Morgan chopper circuit using a suitable reactor in place of the ordinary inductor L is a modified arrangement. So what happens now? Usually L inductor we are using. Example is given as a chopper circuit, that is DC to DC converter. Other than DC to DC converter, Morgan chopper, one of the example, what he has done, what the experiment has been taken care, instead of using a simple L, simple inductance value, he has replaced the inductance with the reactor. Inductance is replaced by a reactor itself. So they could get like examples. What I can give is, I used to create a PPT using Microsoft Office. The same thing can be created using some other Office itself, like WPS Office you are having over there. Correct? No? Your mobile phones is having WPS Office. Though the contents may be different, same. The presentation may be same type, same data you have to present it. How you are going to present, how fast you are going to present, how efficiently you are going to do that. That is very important. So WPS is suitable for your mobiles. Okay. MS Office, Microsoft Office is suitable for as per my convenience. I am doing that. Some of them instead of PPTs they may go for PDF also. Presenting the PDF. Okay. Already they created using some other type of the document. They made it as a PDF and they presented it. So Morgan chopper also, that is one of the chopper DC to DC converter, is mentioned for one type of application where the inductor was not suitable. So what he has done, instead of inductor, he has replaced that by a reactor and you could get the outcome for that. Advantage of your class B commutation is longer oscillation period and more assurance of the commutation. We will get the longer oscillation period, means there is no much oscillation, there is a longer oscillation period will come over there. Turning on, turning off, you can get it. Commutation component does not carry the load current. So one of the advantages is no load current. The L what we are having, no RL does not carry the load current because they are separate. They are separate. Here, this commutation component, these two are separate than your your load. But in the previous circuit in the class A commutation, they are in series over there. So they are carrying the your L and C will be carrying the load current also. But here N and C they are not carrying the load current. They are not carrying the resistance which is connected over there. So this is with respect to class B. Okay, class A also I explained, class B also I explained about it. So that is with respect to just 1 second. Any clarification is required with respect to this topic? So class A, class B both are finished. Class A, class B both are finished. Now we have to move on to the next topic. Next topic is, it is third chapter. Chapter number 3. That is your gate trigger circuit. That too in chapter number 3, it has been not directly given from 3.1, 3.2, 3.3. It is directly they have taken into 3.5. 1, 2, 3, 4 is not there. 3.5 up to 3.52. Then 3.6 we are having. Gate triggering, we know different types of triggerings are there. One is by using the simple R circuits, other one is by using this simple RL circuit, RC circuit, and third one by using the UJT. 3 different types of gate triggering. We will see how exactly gate trigger is going to be done. Okay. Next topic is gate triggering. That is chapter number 3. I want to trigger my circuit. I want to trigger my thyristor. I want to give a firing angle. How to do that? I want to give a firing angle for your thyristor. There should be a circuit. Using that circuit only, I can trigger my gate. So there are 3 different ways of triggering your gate of a thyristor. One is by using a R triggering, second is by using a RC triggering, and third one is by using UJT triggering. So we have to see one by one. What do you mean by R triggering? What do you mean by RC triggering? What do you mean by UJT triggering? Here, R triggering, R resistance triggering, we'll call that. See here, this is the resistance behind the thyristor here. This is a thyristor. Okay, this thyristor, the gate current can be given to your SCR by using a load RV. By using RV, we are going to do that. We are having a AC signal, we are having a load, some minimum constant value of R is being given, and this is where your resistance, which plays a very important role, which can generate the trigger current IG, which can generate the IG, and which can trigger your SCR, so that your circuit is going to get work over. So here we are having, this is E, we are having ES, that is source, and ES, it is a pulse, like AC signal we are having, and EL, this is a load, there is a load is been connected over there. EL also we are able to plot. EL, when how we are going to get EL is very important. Until you give the gate pulse, until you give the gate, your SCR will not work. SCR will not work at all. There should be a gate current should be there. Until you give the gate current, it will not work. Once it gives the gate current, then only your real work and you are going to get this. This is what your SCR triggering long back we have discussed about how exactly SCR triggering comes into picture. Initially, I wrote on the board, very few were there at that time. I have given you the diode characteristics, simple diode characteristics. If it is not diode, if it is SCR, there is a triggering pulse. This is right from 0, it will not start. You should have an IG, that is gate current. After that gate current only, it's going to get triggered. Similarly, on VAK, there is voltage across this. Voltage across this will be measured in terms of this particular waveform. So when it is 0, voltage will be increased up to the triggering current. Once the triggering current comes into picture, voltage will drop to 0. Voltage across the anode cathode is going to be dropped to 0 itself. Now, this has been explained in detail, theoretically. Simple method for varying the trigger angle and therefore the power in the load. So, R triggering is the simple method. Resistance triggering is one of the simplest method where you can trigger your thyristor. Okay. SCR gate current is supplied by an AC source of voltage ES through R minimum, RV and the series diode D. What happens? The signal, this one, which has been supplied to your thyristor through load, R minimum, RV and diode. Okay. Here I am getting ES, that is source voltage. It will be supplied, the currents will be supplied here. It has to be supplied to the gate. How it will be? R minimum, RV and diode should be in forward bias. Then only your I will get generated. So that is the first step. SCR gate current is supplied by an AC source, okay, through R minimum, RV and the series diode R, diode D. Okay, I am getting a current. Now, if I am getting a current, as ES goes positive, the SCR becomes forward bias from anode to cathode, but it will not work until you apply the IG. I told them. See here, I am having ES positive. It is passed through the load. Load is also there, but it's passing here. Since there is no anode current, gate current. Since there is no gate current, it will not be. Though it is forward bias, it will not conduct. Until I give the IG, it will not conduct. That is why we are not getting any voltage across the EL. Any voltage across the EL. Once the gate current is applied, then only you are going to get the voltage. That is one is explained. It will not conduct because EL is 0 until its gate current exceeds IG minimum. Minimum current should be there before, then only it can. The positive ES also forward bias the diode and the SCR's gate cathode junction. This causes the flow of the gate current. So once it has been positive, once the IG has been given, then it's going to become positive. Gate current will increase as ES increases towards its peak value. Gate current is keep increasing over there. So that's why we are going to get as E maximum and here also EL also will keep on increasing. Gate current increases. As gate current increases, it's going to conduct it. Since it is conducting, I'm getting the voltage across the load. Now, theoretically we are explaining this. Practically we have to do this. Practically you have to expose into this. So I need a ES AC signal from the frequency generator. I'm going to function generator. I'm going to give some frequency, some around 500 hertz or 1 kilohertz frequency, some 10 to 10, big 0 to plus 10 to minus 10 amplitude I'm going to give. Then connect the load, connect the thyristor, connect the R minimum, connect the R low, this one variable resistance, DRB, keep changing over, keep changing. Then see what is the current you are going to get. Definitely this waveform you are going to get. This is where you are supposed to. I can go for your Lush projects. Using Lush project, you can design this. But I need to select minimum value of R and minimum value of this variable resistance. I can go for it. This is B. When IG reaches a value equal to IG minimum, the SCR turns on and EL will approximately equal to ES. Okay. That is what has been given in the waveform. SCR remains on and EL is approximately equal to ES until ES decreases to the point where the load current is below the SCR holding current. So IL has decreased when the ES is decreasing, when the source current voltage is decreasing, obviously your current also keep decreasing over there. This usually occurs very close to the point until ES becomes 0 and begins to go negative. Because it's a AC, it's keep on increasing and decreasing. It's crossing the 0, it will go to negative. SCR now turns off and remains off while ES goes negative since its anode cathode is reverse biased and since the SCR is now on open switch, the load voltage is 0 during this period. Definitely. See, that is what they have mentioned. The load voltage is 0 at this case. Because it is negative, load voltage is 0. It is somewhat similar to your half-wave rectifier. But half-wave rectifier only using diode, you will get full half-wave you are going to get. But if you are using SCR, you will get until you apply the gate voltage, you will not get that. This is also half-wave rectifier only, but gate current should be applied over. I need to apply the gate current. The purpose of the diode in the gate circuit is to prevent the gate cathode reverse bias from exceeding a peak reverse gate voltage. See, you might have question why this diode is required. Why this diode is required? Diode, what it will do? It will allow only DC. It will allow only DC. Okay, switching is just like a switch. If it is forward bias, then it will conduct. Whatever you are applying, it passes through that one itself. Okay, forward bias just like acting as a switch in this case. The purpose of diode in the gate circuit is to prevent the gate cathode reverse bias. Gate cathode reverse bias. Okay, if it exceeds, okay, from exceeding the peak reverse gate voltage during the negative off cycle. So for that purpose, only for the negative off cycle it's going to work. Diode is chosen to have a peak reverse voltage rating greater than the input voltage Emax. Diode is chosen to have a peak reverse voltage rating greater than the input voltage Emax. So there should not be negative voltage supplied to a thyristor. So to avoid that one, there should not be any reverse voltage or reverse current should flow through the thyristor. We have selected a proper diode voltage. Load voltage waveform can be controlled by varying a RV. Can vary, that's what voltage, that is variable resistance we call that one, which varies the resistance in the gate circuit. If RV is increased, the gate current will reach its trigger value at a greater value of ES, making the SCR to trigger at a later point in the ES. That is somewhat common. If RV is made larger enough, the SCR gate current will never reach IG minimum and the SCR will remain off itself. That is also one threshold. Because RV you have to suitably have to set that one. You keep on increasing, so you will not get the current to your gate itself. See, very simple. As the resistance increases, current flow decreases. As the resistance increases, current flow decreases. If the current flow decreases, means your gate will not get the current at all. So you should select a suitable resistance value, variable resistance value, such a way that the minimum current are greater than the IG minimum, it has to supply to that one. If it supplies more, there is a problem. If it supplies less also, gate current will not be supplied to your ICR. So suitably, a variable resistance has to be kept. That is why I think one of the example experiment what we did, variable resistance we have used. Zener diode characteristics we did there. Okay, we set the variable resistance suitably, such a way that how many of you have done Zener? They will come to know that one. Suitably, you have to set the resistance value, then only your Zener is going to get triggered. Okay. Similarly, SCR also, you should have a proper load variable resistance where your proper current will be given to gate and gate will be triggered and SCR will conduct. Limited resistor R is placed between the anode and gate so that the peak gate current of the thyristor IG minimum is not exceeding. Why R minimum? That should also has been given. When supply voltage has reached its peak, Emax divided by IG minimum is R minimum. Stabilizing resistor RB should have such a value that the maximum voltage drop across it does not exceed maximum possible gate voltage, that is VG maximum. So RG, that is RB, should be less than or equal to your variable resistance and minimum resistance multiplied by your VG maximum divided by your EDC plus E max minus VG max. So how to calculate the RB? Where is RB? Here. I need to calculate the RB also. R minimum I have kept. RB also, it's a variable resistance. RB need to be calculated. It should be less than or equal to, variable resistance plus minimum resistance multiplied by the VG max divided by E max minus VG max. Okay, that is gate voltage, maximum gate voltage. Once you know this, you are able to identify the R value. See here, the question may rises like calculate the RB value for a suitable resistor. They may give a SCR, they may give the R minimum, they may give the R value, that is RB. You have to find the RB. So you can easily supply this equation, you can apply and you can calculate and you get the what should be the RB value. So very simple, any circuit if you are designing, all the components should be precisely how to select it. If you don't select it, you will come into a problem, means you will not get the proper output. The problem why we are not getting in the lab means because there is no proper calibration of the components. We know 10K, but when you are measuring, it's not showing 10K, it's showing 9.8 or 9.7 something, it's showing over there. So it's not properly calibrated to 10K exactly. Theoretically, we'll say it is 10K, but practically we are not getting 10K. So we are getting some fluctuation in the outcome of this. But it is acceptable. 10% is acceptable. Thyristor will trigger when the instantaneous voltage ES is. When the thyristor will trigger, depending on this particular equation. When the thyristor will trigger is ES should be the ES value. That should also, you should check it out. ES value also you should check it. It is keep on varying 0 to maximum, maximum to 0 like this. When it is getting triggered with the IG minimum, RB plus R minimum plus VD, that is diode voltage, and VG minimum. This is VD means diode voltage. Whichever the diode which is connected over there for the forward bias operation, there is some voltage drop across the diode. That should also be known. It may be 0.3 volts or 0.7 volts depending on the diode, depending on the silicon or germanium. Okay, 0.3 volts, it may be 0.7 volts, it may be. So that value you should calculate. Advantage of R trigger circuit is that it's simplest and most economical, but the disadvantage is trigger angle alpha is greatly dependent on the SCR's IG minimum, which depends on the type of the SCR and high temperature dependence. There is one disadvantage. Low voltage waveform can only vary from 0 to 90 degree. You cannot vary beyond that. 0 to 90 degree only you can vary. Beyond that you cannot go further. That is with respect to your R triggering, resistance triggering. Second type is resistance and capacitance triggering. Where we are using, previously we are using only resistor, and now we are using capacitance also. Okay, this is resistance capacitance firing circuit. See the thing here, it is going beyond. Previously it was only up to the 90 degree. Now it is beyond 90 degree. It's coming over there. See, 0 to 180 degree. That is the difference. Previously, what is the advantage? It cannot go beyond 90 degree. Which one? R triggering. But RC triggering, it can go 0 to 180 degree. 0 to 180 degree, it can go for that one. That is what one of the advantage with respect to your RC triggering is. I'll explain the equations later because I want you to know what is the difference between RC and R triggering. That's why I have shown the diagram and also what is the difference between them. But how exactly it's working, what are the parameters we have to take, what is the suitable components you have to take, what is the values, we'll explain that in the next class. So I'll be completing this. 1 hour is sufficient for both RC and transistor triggering. Then we can go for the phase control converters, that is choppers, different types of choppers, step down, step up, and all those things will be easy. Converters. Last 4th module is easy. Voltmeters, multimeters, and all. 3rd one, that is also okay. Classification of single phase, half bridge, full bridge rectifiers, you have studied. Once the first module is fully thoroughly, if you know, then it will be other modules are easy only. Next modules and all based on the first module only, it will be covering.